Welcome to the second practice examination. This is an adaptation of the December 2018 Predictive Analytics exam. The original version used a different exam format, and since then the SOA has changed the format to be more specific. So I've gone back and made this exam a little bit easier, as well as to change the format so that it's in the most recent version. So to start, you'll have two files, a Word document and an RMD template. The first step is to read over the entire project summary. On the actual exam, you will have a printed out copy of the problem statement, which will be separate from the Word document. In this case, I've included the project statement in the Word document just to make this process easier. I'm not going to read all of these words in the video. However, a good strategy is to read over everything before making any decisions or running any code. So just from a high level, the overview is you have two assignments. The first is a list of specific tasks. In this case, it doesn't matter what type of language you use. You are not graded on professionalism or aesthetics, but simply on results. On the second phase, when you write the executive summary, professionalism, grammar, and aesthetics can technically be graded. The SOA says that they will run your R code. However, I haven't seen anyone or heard of anyone who has had points taken off for not having code that's runnable. However, if there is a blatant error, or if you do create something in the final document that cannot be recreated in the report, in the R file, then I could see that being a problem. However, I don't think that you need to go back and rerun your code really before submitting the final report, as long as there are no mistakes in the final report. So the business problem is that a miners union would like to give functioning mines in the U.S. a simple 5-star safety rating to help their members when choosing where to work and negotiating hazard pay. They think they have a good understanding of what factors drive mine safety, but they want to offer an independent, data-driven analysis that can validate and refine their options. So the object is really interpretation. They want statistical inference. They want to understand the business problem. It's not a problem of predictive power or model performance. The data is over a few years. You have 20 variables, which is rather a lot to look through in a 5-hour exam. From a high level, the specific tasks are going to be just summarizing the data, exploring the target, deleting records, looking at average injury rates per year, so just looking at graphs, examine box plots, split to training and test, fit a decision tree to predict the number of injuries per 2,000 employee hours, and there are some details as to how to do that. Measure the performance of the model, consider alternative approaches, and write an executive summary. And here's the data dictionary of all of the variables. So in terms of time, you want to be spending your time in proportion to the points of each question. These small tasks are only a few points, so get through them as quickly as you can. These larger tasks like fitting the model and writing the executive summary are 40% of the exam. So that is where I will be focusing my time. To start, I'll just load the libraries. And it says write a high-level summary of the data. So I suggest you name the data to something simple so that you don't need to type out something repeatedly. So I've just changed the name to data. Here are the variables. So I want to immediately start writing out the summary. So I'll say R53 of injuries. And I might just, I might not say everything that I'm typing. I might just type instead, and you can probably read what I'm saying. Each row represents a mine during a single year. So that means that there are 50,000 mines. The variables are related to the type of mine, the type of ore extracted, the mine status, and the percentage of hours that employees spend in different areas. So these are the percent hours on surface, on the strip, at the auger, cumulative bank, dredge, other surface, etc. And the target variable is the number of injuries. So the target, actually I don't need to say this because this is the next question. So all that they were asking was to write the number of records, the number of variables. Done. Explore the target variable number of injuries as well as employee hours total. So here I want to only do what they tell me to do. So they say look at the average, max, minimum values and comment if they make sense. So this is task 2. I want to say data, num injuries, and then look at the summary. Okay, so the number of injuries goes from 0 to 86. With most mines having no injuries. Also look at a count. So you say data count injuries. Here you can see 45,000 injuries. 45,000 mines have no injuries. So there are a lot of zeros in the data. Let's create some histograms. So I'm going to use ggplot in order to create these histograms. And here you can see that most of the injuries, most of the mines have 0 injuries. I'm also going to look at the log of the number of injuries because it's often the case that these variables get a log transform applied to them. And I can just apply the log function directly in the ggplot call. So here's the log of the number of injuries. It's still right skewed. And here, if you have a value which is 0, it's still shown as 0 in the graph. So all that they ask for is this histogram. So I'm going to right click and copy. And if you're on Windows, you might have a difficulty because if I try to copy and paste directly into the Word document, it doesn't work. And so I have to copy into Microsoft Paint, and then I can copy into the document. So they ask for num injuries as well as employee hours total. So that's this column, employee hours total. Say it makes sense that most mines have no injuries. Okay, and the formatting here is slowing me down. The employee hours goes from 1 to about 6 million, with an average of 35,000. So the median is lower than the mean. This means that it's right skewed. Yes, indeed. The distribution is right skewed. Okay, and let's see. Is this all that they ask for? They also ask for the percentage of mines that have no injuries. So I'll do a quick calculation. So I want data, and then I want to summarize. So I want %0 is equal to this sum if num injuries is equal to 0, then 1, else 0. And then I want, this will give me the total number of injuries that are 0. If I want the percentage, I just divide this by the number of records, which you can get from using just the n function. So that's 84%. 84%. 85%. Let's just say 84.8% of records have no injuries. Task 3, delete records. So on the actual December 2018 exam, there was more data cleaning and it took a long time. So I've made this simpler. Delete records where mine status is not active or full-time permanent. Okay, so what is mine status? So if you just look at the data, I just look at the head, you can see each of the columns, and I want to find where's mine status. These are percent. There it is, mine status, so full-time permanent. If you want to quickly see all of the values, you can just do a count of the column, like so, and you can see there are 8 possible values. So I want to delete records where they're not active. So I want to filter, and I want mine status to be in active or full-time permanent. Okay, and I also want the total number of employee hours to be less than or equal to 2,000. So employee hours total, less than or equal to 2,000. Done. Now let's see how many records there are. there are 746 records. That is a large reduction from the beginning. So something must be wrong. Let's see which of these is causing the error. Okay, so if I oh, I see what I was doing. Okay, so I want to be deleting records where there are less than or equal to 2,000 hours. So that means that I want to filter so that employee hours total is greater than 2,000. Okay. This results in 24,000 observations remaining. That's a lot. It's about 50%. However, we only care about mines which have a high volume and which are active. So I'm going to save this as the data. So I'm rewriting the data object as this version which has these records removed. And then I'm going to fill this in. So after deleting these records, there are how many rows? Dimension data 24,000. 24,348 records remaining. Okay. Task 4. Look at the average injury rate per year and comment if there is a trend. So what I want to do is say I want one row per year, and I want the value to be the average rate. So I want to group by year, and then summarize so that average rate is equal to the total injuries over the total employee hours. Oops. But this is per 2,000 hours. So I want to multiply this by 2,000 hours. So I can see for each year, for 2013, there were about 2.7 injuries per the injury rate per 2,000 hours in 2013 was 2.7%. And in 14, it was 2.7, 2.5, 2.4. It doesn't look like there is a clear trend based on this. So I want to copy this into Word. So I'm just going to copy this text and paste it, and then say, based on the average, I'll just say, there is not a clear trend in the average injuries per year. Task 5. Examine box plots and comment on which variables are likely to be most predictive of injuries. Explain how this is different than a variable causing injuries, i.e. correlation is not causation. Okay, so here they give some code to create a box plot. And we're supposed to be looking at graphs for type of mine and commodity. So we're not looking at all 20 variables, only these two variables. So here, for instance, is how to create the graph with type of mine. So you can see on the y-axis distribution for each mine, and it looks like the underground mines have higher injuries The other types of mines have lower injuries. So let's just copy this. And then put it into the document. And then add some commentary. The underground mines have the most injuries. The other types of mine have fewer injuries. This is different. This does not imply that being having a mine being underground is causing the injuries, as we are not accounting for other variables. So, for instance, it could be that these underground mines are somehow working in more dangerous conditions, or they're in less healthy environments. So we can't really get causation without considering other variables as well, such as if we were to fit a model which accounts for these levels. Okay. So now I just have to do this again, create another box plot for commodity. Here's commodity. And on the actual Prometric computer, I do believe you can just copy and paste directly. You don't need to do this intermediate step going into Microsoft Paint. So here, the coal and metal mines have the most injuries. Sand and gravel and stone mines have less injuries. Step 6, split into training 80% and test 20%. So they give code here to set this up. And I don't know what this function does exactly, right? In general, it's a good idea to not trust any code that they give you verbatim, because part of what they're testing is your ability to understand code that someone else would give you. So in this case, they say use 80%, 20%. However, if you look at this parameter p, it's saying p is equal to 0.75. If I look at create data partition, this function, in our documentation, I will see the value p is the percentage of data that goes to training right here. So the way I got here, again, is I just typed question mark and then the name of the function that I wanted to see. So if I wanted to see another function, like this dim function, let's say that I didn't know what this did, I would just type question mark dim, and this gives me information on that function. So in general, try to be very skeptical of any code that they give you. In this case, they said p is equal to 0.75, but the actual question asks you to use 0.8. So I'm going to change this to 0.8, and then I'm going to tell the grader that I did that. I noticed I changed the value of p to be 0.8 so that caret would use 80% of the records training. Done. That's the 5 points that they wanted you to get. There's nothing else challenging about the question. You can look at the dimensions to see that these are actually 80%. Task 7. Okay, this is the modeling question. Fit a decision tree to predict the number of injuries per 2,000 employee hours. Poisson regression. So in Poisson regression, you are using a linear model. Poisson regression is useful for modeling counts of data when X is the matrix of predictor variables, F is the decision tree, and E is the error term. Okay, so in Poisson regression, you say the log of the number of injuries over employee hours times 2,000 is equal to F. Okay, where F can be any type of model. I said Poisson regression really is referring to a linear model, but this structure can work with F being a decision tree, or F being a GBM, or F being a random forest, or F being any other type of model. In this case, they say fit a decision tree. So that means F is a decision tree. But from this abstract level, it doesn't really matter. So if you take the log of these two, you can say log of number of injuries minus log of employee hours, and you add it back to the right-hand side, which is what they've done here. And so this is called the offset term, where log employee hours is the offset. In the R-part library, they tell you how to do this. It automatically takes the log. Okay, we give it this name because its value is already known. So this is some content which you might have remembered or you might not have remembered from the modules. But the challenge of this question is really on interpretation. They want to give you some documentation or some type of math formula, and they want you to understand it and to correctly apply it to the problem. In a few sentences, describe what a decision tree is and how it works from a high level. So they're not asking you to do anything, they just want you to describe a decision tree. Okay, so a decision tree is a series of yes/no questions which create buckets of observations and each bucket predicts the number of injuries for that group. Trees are useful for getting simple approximations and understanding the problems they detect. They are able, well, yes, it's just saying describe how it works. And I think that's sufficient. It's just a series of yes/no questions, which break up the data into partitions or groups. Use the target variable number of injuries with employee hours total as per 2,000 employee hours being the offset term. So here's the code that they set up. So first they set the random seed. This just ensures that if you run this code again, the random generator that's used to create the decision tree will create the exact same decision tree. And here's the formula. Let's make this a little bit wider. Okay, so this is it's creating a new data set, train D-tree, and it's selecting these variables: injuries, year, commodity, seam height, etc. And it's doing this for training, and then testing is just selecting the same variables from this. So it's just doing this. It's just selecting these same variables from the test data. And it says, warning, including all of the percentage variables will result in an overdetermined system. This means that some columns are linear combinations of the other columns, and it will break some models. This was a trap by the 2018 version of the SOA exam. For instance, if all the percent columns are included, then percent total is just percent underground plus percent surface. you press all the other percentage columns. And so if you try to fit a model, it says error. So to fix this, basically, I'm just giving you this for free so that you don't run into this mistake, so that you know not to include all of the percentage columns at once. So in this case, the code is excluding percent surface. This is fine. You don't need to change it unless you really want to. So here's the code that creates the tree. So it's using the rpart library. And this is basically taking the employee hours total and the number of injuries as the offset term. And then it's using all variables. That's what this dot refers to, except it's subtracting employee hours total. So it's not using employees hours total as a covariate, but it's using all of these other variables. Now, if this seems complicated, you can rest assured that this is the exact code that was included on the 2018 December exam. So it's very likely that the SOA will try to make something that's difficult to understand, so that you have to do a little bit of work in order to figure out what it's doing. So I want to look at this rpart function, and I can see what the default values are here. So this is the formula argument. It says formula is the first argument, right? And then I can also see data, okay? I can see method. What does method do? Method is one of ANOVA, poisson, class, or exponent. If method is missing, then the routine tries to make an adjustment. Okay, so what are we doing here? We're supposed to be doing poisson regression, right? Because we're modeling a count, the number of injuries. So this is set up to be ANOVA. It really should be set up to be poisson. And then they give you the parameters min bucket, complexity parameter, and maximum depth. Okay, and then they prune the tree, they plot it, and they make some predictions. Okay, let's just run this section and see what it does. Okay, it shows you here the error against the complexity parameter. It shows you the tree, which is using the commodity variables, employee hours variables. Okay, and this is, so the question says employee hours is being used as an offset. Okay, so it's really asking you to use Poisson regression. So when I'm going to keep the default code here, and then I'm going to create my own version below. So I'm just going to copy all of this. I'll just get the model part. I don't need to recreate the data. And we're going to put this into a new chunk. And then I want to change this to Poisson. And then rerun. And I'll just keep, yes. So let's rename this. Let's rename this to tree 2. Actually, no. I'll just rename this to predictions 2. So predictions 1 up here will be the default predictions. Predictions 2 will be the predictions from the Poisson tree. And maybe I should rerun this chunk again, just so that I don't save as the wrong object. Okay, so now I have Poisson predictions and the baseline predictions. Now what do they want? So they want you to calculate the log likelihood. So there was a function here there was a function here which calculates the log likelihood. Here it is, right? So this is task 8, actually. Well, let's go back. So I'm kind of doing a few different things at once. So I noticed that the code was using ANOVA as the splitting criteria, whereas it should be using poisson, as this is modeling a count variable. So if you were just doing ordinary regression and you were just predicting like a claim amount in each bucket, then using ANOVA would be appropriate. However, because we're using we're modeling a count, using poisson is appropriate. So that was the only change that I made to the code, right? Measure the tree's performance, 10 points. So the December 2018 version of the PA exam gave students a function that calculates the log likelihood based on a Poisson model for the number of injuries per 2,000 hours. This was used to compare models. Okay, so 2 questions. Is the decision tree showing improvement in the log likelihood rather than using the average? And what about predicting no injuries or all zeros? Okay, so here's the function, log likelihood. And here's how to calculate the log likelihood using predictions 1, the predictions from their ANOVA tree. And the log likelihood is negative, which is entirely possible. So let's create the predictions. Let's calculate the likelihood for predictions 2, and that's positive. Recall that likelihood is better when it's higher. It's like a probability. And so when you have the log of a positive number, you still get a positive number. So higher log likelihood is better. So is the decision tree showing improvement rather than using the average? So how do you get the average? Use the mean function. So if I use the mean of train, oh, actually, let me rephrase that. Let's say, how do we get the average number of injuries? We have to take training and summarize to get average is equal to the total injuries over the total employee hours. That's this number here, and we want to multiply by 2,000 because we're predicting for 2,000 hours. So it's 0.026. Okay, so if I want to predict the log likelihood against where the average is used instead of a prediction. So in other words, for every single mine, just say that the predicted injuries is 0.027, right? Then calculate the log likelihood. That is a very negative number. Here again, you can see, let's get rid of this for a second. You can see using the first ANOVA tree is bad. Using the Poisson tree is much better. Using an average is still bad. And what about using 0? That's even worse. So we can just summarize this. The model performance from each model is below. The tree that we fit using Poisson regression is best, as this has the highest log likelihood. Here's ANOVA tree. Here's Poisson tree. Here's average. All zeros. So it's a little bit tedious sometimes to copy and paste numbers into the document, and so I'm just going to type them out. So the ANOVA tree is minus 2128971. The Poisson tree is 549. The average is minus 15715. All zeros are minus 59917. Again, the formatting here does not matter. They're just looking for numbers. If you have, if you have the right values, this is all that matters. Okay, so expectedly predicting all zeros or predicting the average are worse than using the model's prediction. Okay. Task 9, consider alternative methods. List a few pros and cons of using a decision tree instead of a different model, such as a linear model, GLM, lasso, or ridge, or a nonlinear model, random forest, or GBM. So this isn't asking you to do anything. They're just asking you to list a few pros and cons. So they're basically testing your high-level understanding, your knowledge of the statistical concepts. So this is one of the questions which you will either know or not. So just memorizing the high-level pros and cons of different models is a good way to approach these problems. So the advantages of a decision tree are interpretability, detection of interactions, missing values, and non-linear relationships. It can be converted into a spreadsheet or just a simple formula. They work. I think that's enough. That's sufficient. Disadvantages are weak predictive power, which doesn't matter in this case. Limited, well, I'll say predictions are non-continuous. And so it's possible for small changes in the inputs to result in drastic prediction changes due to each prediction being an average of the number of injuries in that bucket. In other words, if you look at the decision tree, it just means that if sometimes if you have a simpler tree, like is this the Poisson tree? This is the Poisson tree. it means that the predictions can jump around drastically because these are discrete values on the terminal nodes. Once I look at this tree, I realize that this is far too complicated for our means because the emphasis here was on interpretability. So this is basically wrong. I need to revise this. So I need to make the tree simpler. So right now the maximum depth is set at 20. Let's try turning this down to 5. Let's see what happens. Because we want to make this tree shorter. Okay, that helped a little bit. CP is 0. Complexity parameter is the penalization parameter. It's like lambda in a lasso. So the higher the value, the more penalization. So if I turn it up a little bit, still complicated. Minimum bucket is the number of observations which are allowed, the smallest number of observations which are allowed in a terminal node. So I can turn this down. Let's turn this down to 10. Actually, let me rephrase that. I want to turn this up so that you have a stubbier tree. This is still somewhat complicated. We'll try turning up the CP value. Okay, this is getting easier. This is just down to a few variables, which is easier for the minors union to interpret. So this is just using percent hours, percent strip, seam height. For our cases, I'm just going to keep it like this. So I just need to revise the log likelihood. So again, this was predictions 2. So if I just rerun this code and look here, it's now 487. So this is just 487. Still much better than the other models. Okay. So the disadvantages were weak predictive power. Predictions can be stair-like. Requires a large data set. Easy to overfit. I think that's enough. Well, I'll just say, yeah. To training. Okay, and they also said pros and cons of decision tree instead of a different model, such as a linear model. So if I was using a linear model, I would need to be automatically hand coding interactions and nonlinear relationships. Decision trees also can perform variable selection. Performs variable selection, which linear models can do as well with ridge or lasso or elastic Linnet. It's more interpretable. Random forest or GBM would have more predictive power at the cost of interpretability. Disadvantages of using a tree are really just coming down to predictive power, and also yeah, I think this is fine. There aren't really any wrong answers to these types of questions as long as you are correctly listing enough bullet points that the grader will give you credit. I don't think you can lose points for including too many things, but you can lose points for not including enough. So a good strategy is just to write down everything that you know. Okay, so task 11, executive summary. This is 20 points. So non-technical language, write a summary of tasks 1 to 10. and interpret the decision tree in plain English and briefly explain how it can be used to create a safety rating system. So think of this as an English essay instead of a predictive modeling problem. So I have to go back to all of these tasks and summarize what I did and the problem statement. So the business problem is the mine would like to give functioning mines a 5-star safety rating. So the goal is interpretability. The objective of this analysis is to understand why miners get injured and to pass this information on to the miners' union in the form of a safety rating system. There are many types variables to consider, such as the type of mine, the activity level, the type of ore used, and so forth. This study accounted for 20 different variables and predicted and identified the leading causes of injuries using predictive analytics. The data. So this was just the business problem here, this first paragraph. Next paragraph is going to be the specific tasks. So I summarized the number of records, the variables used, explore the target variable. So now I'm on task 2. So the target that we used, well, let's just say the data consisted of how many thousand variables were there? 50,000 observations. Mines. So these are individual mines collected from, I don't remember. So if I don't ever have a question about the data, I can always just bring up R and look. So I'll just do data year summary collected from 2013 through 2016 for each mine. The number of injuries were recorded. We noticed that most mines had no injuries. It was 84%, right? 84%. Because each mine has a different number of employees working, we modeled the rate injuries per 2,000 hours so that low volume mines will not over-represent will not skew the results. Okay. What else did we do? We deleted a lot of records, right? We deleted records until there were 24,000 remaining because we don't care about the inactive mines or the mines with fewer than 2,000 hours. So we removed inactive mines as well as those with a low volume, less than 2,000 employee hours, which resulted in 24,000 records remaining. Okay, next task. Look at the average injury rate per year. We saw no trend in the injury rate per year, which is important. Why is it important? Because if there was a trend, then this would need to be accounted for in the model. Otherwise, we would be modeling a time series. Task 5, examine box plots. We saw that most underground mines and mines with coal or metal had the most injuries. Coal and metal mines and mines that were underground had reported the most injuries. Task 7, fit a decision tree. So again, this is a non-technical summary, so the most that you want to do is just describe what the model does or why you chose it. We focused on making these results interpretable, and so chose to use a decision tree model. This breaks the problem down into simple yes and no questions, which are appropriate for a safety rating system to ensure that the model will work in real life. We used a holdout sample approach where the model was trained on different data than it was evaluated on. What else did we do? We fit several different models. We fit the Poisson model. We fit the ANOVA model. The model selected was one of 4 candidates, right? Because we selected the average and had the best performance. What else did we do? We found that Poisson regression was most appropriate because I don't need to mention Poisson regression because this is really non-technical. They will have no idea what a Poisson model is. So measure the tree's performance. We talked about this. Consider alternative methods. So we have to interpret the model first. So let's go back and get the plotted tree, which is right here. I'm going to copy this, go to Word, go to Paint, copy it again, and it's not really appropriate to include a decision tree in this, executive summary because this is supposed to be a business report. So here I'm going to create a bullet that says show the decision tree. And here's the plot. They will almost always ask you to include the graph of the decision tree. And now I want to translate this into English. So, okay, the findings, or I'll say this, we suggest a safety rating algorithm as below, which can predict which mines are likely are at the highest risk of injuries of workers having injuries. So these are mines where now I just look at the decision tree. Percentage mines underground are greater than 0.64. If that's the case, then this is a relatively high risk. There are a lot of injuries. The injury rate is 0.046. If there are fewer than 0.64, if fewer than 64% of the hours are spent underground and more than 45% of the hours are on the strip, then the injury rate is 2.5%, and so forth. So these are the high risk individuals on the right. That's why this is a darker color. On the left, these are the low risk mines because these are, you can see the injury rate is lower. So high risk are percentage underground, so more than 64% of hours are spent underground. And then moderate risk is fewer than 64% of hours spent underground, but more than 45% of hours spent on the strip. I'll say low risk, or I don't know. I'm just making up these categories. Low risk, it's going to be fewer than 64% hours underground, fewer than 45% hours on the strip. So so fewer than 64% of hours underground. So yes, fewer than 45% hours on the strip. So again, yes, and then seam height, and have a seam height of less than 37. Let me just double check. I might be getting these backwards. Okay, so if you have a yes, you go left. If you have a no, you go right. So percent hours underground, less than 0.64. Percent hours, so if this is actually less than. Oh no, because if it's less than 64% of hours spent underground, this is a no. So that means that this has to be more than 64% of hours underground. So this first point is right. Moderate risk, so fewer than 64% hours spent underground. So that's a yes. More than 45% of hours spent on the strip. So if it's yes, you go left. If it's false, you go right. So this is actually fewer than. And fewer than 45% of hours spent on the strip. So that's this category right here. And then fewer than 64% of hours spent underground, more than 45% hours spent on the strip. So this is going left. and have a seam height of less than 37. That's low risk, and I'll just say these are whatever are safe risk. This is the far left category. So I'm going to copy from before and then say have a seam height of more than 37. Okay, so that's the translation into English of the decision tree. So using these ratings, you can create a decision tree. Right? Okay. Is there anything else that we should include? At this point in the exam, it's a good idea to go back and to just see if you've included all of the output that the grader expects. So again, I'll just do this here so that you can see. So write a high-level summary of the 5 data points. So here's the high-level summary. I have the number of variables and I have the sample size. Check. Explore the target variable, num injuries, and employee hours total. Okay, so look at the average, max, min. So here I have the max and the min. I have the average. And these make sense. These values make sense, are reasonable, as we don't expect most mines to have injuries or anything. So the percentage of mines that have no injuries. Yes, 84.8%. And then I also want to do this for employee hours total. See, this is number of injuries and employee hours total. So I don't have a histogram for employee hours total. So here's an example of why it pays off to go back and to review the simple things. So let's go back to the histogram. There it is. Not sure why this isn't working. Oh well. Okay. This is employee hours total. Is there anything else? This looks good. Delete records where mine status is not active or full-time permanent. We've done this already. Deleting records, there were 24,000 records remaining. Look at the average injury rate per year and comment if there is a trend. So again, this is about 2.7%, 2.5%. There's not a clear trend. How can we check that this is valid? Well, if you look at your decision tree, let's go down, where's our decision tree? Look at these predicted values, 0.02, 0.025, 0.046. This looks reasonable. Examine the plots and comment on which variables indicate the most injuries. So here, underground mines have the most injuries. Coal and metal mines have the most injuries. And really, this isn't that useful at all because this isn't taking into account the hours spent. This is just looking at the number of injuries. This isn't even looking at the injury rate. So I might add a quick note here. Additionally, these graphs are looking at total injuries and not an injury rate. And so so mines which have more volume appear to have higher injuries. Not appear to have more injuries. Okay. Okay. Split data training and test. This is done. You can go back and check if you want. Where's the caret to create data partition? There it is. And we set P to 0.8. And we told the grader that we did this. Fit a decision tree that breaks the number of injuries per 1,000 hours in a sentence. So just look at the bullet points and see that you've gotten everything. In a sentence, describe what a decision tree is. A decision tree, here we describe it. Okay. Use the target variable num injuries and employee hours total for 2,000 hours as an offset. This was set up by default in the code. We didn't have to change it. Include the R-part plot. That's done right here. Just move it up so that it's in the right section. Okay. Measure the tree's performance, 10 points. We have done this here. Consider alternative model methods, using pros and cons of using a different model, such as linear model, GLM, lasso, ridge. So there's few advantages using this tree or interpretability, interactions, missing values can be converted to a spreadsheet. Performs variable selection. A random forest or GBM would have more predictive power at the cost of interpretability. Some of the disadvantages are weak predictive power, predictions are not continuous, requires a large data set, easy to overfit to training data. Executive summary, okay. So it looks like we have everything. We just did a quick scan of everything in the report. I think this is good to go. Now there are some grammatical mistakes here, so I might go through and just do a quick spell check. Again, this is probably not required, but if you have time, it can't hurt. Done. Okay. I think that's it.